we'll talk about vectors. Vector you will be studying in physics as well as in maths while studying 3D geometry and all in maths, and in physics there are many topics where concept of vectors will be required. Before we talk about vectors, let us talk about some physical quantities. Like if we talk of length of an object, we say it is 2 meters. What does that mean? It means an object which is 2 meters long. So just that number 2 with an unit is sufficient enough to define that quantity. Similarly, if we talk of a mass of 5 kg, so that means we get a perception that this is an object which is 5 kg by mass, and generally we perceive by weight, so we say it weighs 5 kg, which is a gravitational unit of this thing, weight. Okay. Now coming to these are the quantities which can be expressed or can be explained by a pure number, so we call them scalar quantities. So these are scalar. There are certain quantities in physics which we'll be using extensively, like the velocity, acceleration, force. When we talk of that, these are the quantities which not only associates a number, they also require to be defined by a direction. So the quantities which requires a magnitude as well as a direction, they are called vector quantities. So if we talk of a force of 2 Newton, that means the force along with its direction should be specified to define it properly. Mathematically or symbolically, we represent a vector by a bar or a line with a direction. So this length of this vector is its magnitude, and the direction defined its direction, which is the second parameter of a vector. We need to define both of them. Before we talk about vector, what we can generally perceive is, like we have seen arrow, a bow and arrow you have seen. Generally it is having a tip, okay, with a circular head, and the rear end of it is usually a star-shaped or square-shaped element which defines two ends of a vector. So that means an arrow has a specific direction in which direction it has to go. The tip has to always move forward. How we represent this as a vector? So if I see the tip of the vector from this side, what we will be seeing? A clear circle with a dot at its center. So this represents the vector is, if we take reference of this board, then this particular vector is coming out of the blackboard. What we'll be seeing from the rear end, like the arrow is moving away from us, we'll be seeing a cross or a star from behind. So that means this particular representation is the vector is going into the blackboard. Okay, let us talk about some mathematical operations on vectors. So we'll start with the very first one, addition of two vectors. Okay, if I name this vector as A, and I have another vector which is like this as B vector. Generally we denote the vector with an alphabet and an arrow on top of that. So if we want to add these two vectors, there are two ways of doing. One method is called Hetal Method. So what is that method? I take this vector B, tail of this vector B is matched with head of vector A. So you are seeing this कि I have shifted this vector B as it is, maintaining its direction and magnitude. I placed it at the tip of vector A, and the tail of vector B is matched with the tip of vector A. So this is the method of Hetal, where we add that, and the resultant vector is represented like this. If I use a different color, this is that vector. If I name this vector as C, then this is nothing but addition of vector A and vector B. Okay, if we want to subtract, that means if we want to consider a negative vector, suppose I take this vector B and I want to find its negative. What does that mean? It means it's exactly same in length, but its direction is just opposite to the original B vector. So this is our negative B vector. Okay, so now if we want to add vector A and B, but negative, we can either say that this is subtraction of two vector, vector B subtracted from vector A, or we can also write this is addition of vector A with negative of vector B. Okay, how we add this? Again, following the same method, we can draw vector A as we have originally drawn. Then we take vector B, which is like this. So this is our vector A, this is our negative of vector B, and by adding them we get this as the resultant vector, which is another vector D. D vector is vector A minus vector B, or you can say vector A added with negative of vector B. There is another method by which we can add two vectors, and that method is called parallelogram method. What we do in that method, we take both the vectors A and B. Suppose this was our vector A and this was our vector B. Now notice how I am drawing the vectors. Earlier we were matching head with tail, now they are matched tail. That means they form two adjacent sides of our parallelogram. When we have these two vectors like that, we need to complete the parallelogram. So I am just drawing hatch lines to get this, adding them. So that is what is your vector C, which we have done here. If you see, by dimension they are equal. Vector A and vector B are added. You can also say that this is our vector B, which I have matched. Tip of vector A and tail of vector B is matched here, or you can do by parallelogram method. Both of them will be giving you the same result, because addition of two vectors will give you a unique vector whose magnitude is unique and its direction is unique. These are the two methods by which we can represent addition of vectors or subtraction of vectors. When we can get resultant of two vectors by adding them, then the reverse of this process, that can we split a given vector to our preferred direction. If we take a planar geometry scenario like a two-dimensional vector, if we talk of, and I just choose a vector like this is vector A, and we want to get this vector decomposed to our preferred coordinate system. So as I said, it is Cartesian coordinate, so we can say this is our x-axis and this is our y-axis. Okay, so when we take a vector from the origin of this coordinate system and we decompose this given vector A to its component along x-axis and its component along y-axis, so this becomes our x component of that vector. We name it as AX, and this becomes the vector along y-axis, we name it as ay. The suffix are used to differentiate them. So that means by adding ax vector with ay vector, we are getting vector a. It's just the reverse process of addition of two vectors. By this method, we are decomposing a vector to its component vector in our predefined coordinate system. Okay. Now let us go to the next level of application of vectors, which is we have done addition and multiplication. First two operations, mathematical operation we do on vector. Let us talk about multiplication of vectors. Okay. If we have two vectors, okay, and we want to multiply them, there are two defined product or multiplication of vectors. First one is called scalar or dot product. What is this scalar or dot product? If we take again two vectors A and B, which are having their specific dimensions like its length and a direction, if we want to take their product, we define this dot product as, because the outcome of this is a pure number, scalar. So on the right hand side of this equation, you will see there are no direction attached to it, but all of them are magnitude by themselves. So it is magnitude of A, magnitude of B, and cos theta. What is this theta? Let me draw a simple diagram. If we have this as vector B and this as vector A, so what is the product of this vector? And the angle between these two vectors are theta. We define projection of, this can be represented in two ways. We say it could be A cos theta into B, where we are talking of magnitude of that, or we can write this as A into B cos theta. If I take component of B vector along vector A, what does that mean? As I have explained before, that it is decomposing a vector to its component vector. So I am taking only the component of B vector along A, and the angle between them is theta. It's a trigonometric relation definition. So this is the length, which is nothing but B cos theta. So I am taking the magnitude of B cos theta and I am taking the magnitude of A. The product of them or multiplication of them is going to give us a pure number, which we call this as scalar product or dot product. This can be represented in different way based on what type of vectors, how the vector is represented. Like as we said, we have done the decomposition of vectors. So if we have vectors in decomposed form, then how we can do that? Before going into an application example, let me show you a space vector or a three-dimensional vector. Okay, what is the space vector? So far we are talking of all the vectors were lying on this blackboard. We have drawn different vectors in different directions. I have shown addition, subtraction, resultant vectors and things like that. If we want to use this same two-dimensional plane or the blackboard as to represent three-dimensional space vector, this is how we generally represent them. Let us consider three mutually perpendicular or orthogonal axis. This is x-axis, this is y-axis, and this is z-axis. First and foremost point, you must remember that these axes x, y and z must be in right-handed system. Otherwise the cross product particularly will get completely opposite, and which is wrong. So what do I mean by right-handed system? If you take your right hand, x, try to imagine that it is coming out of the blackboard, being 3-dimensional, and I am trying to draw it on a 2-dimensional blackboard. So try to understand that x is pointing out to you. What we do, we take our right hand, position the hand or palm in the direction of the first axis, which is x. So now my hand is pointing towards x. I curl my palm, or I fold my palm towards the second axis, which is y. Now you can see that my fingers are pointing towards y-axis. In that condition, if I extend my thumb, that is what is going to define the direction of the third axis, which are mutually orthogonal. Remember this carefully, that these 3 coordinate axes must be right-handed. I am using my right hand to explain that. This can also be explained by using right hand corkscrew system. What we do, if we want to rotate x-axis towards y-axis, how the screw will be moving. If this is how I rotate a screw, it will be progressing upward. So this is what is called a right-handed system. Now let me take, this is a vector P. Okay, this is a point P whose position vector we always refer with respect to the origin. This is what is the vector. If I take projection of this vector in different plane, let me take it like this. This is what we get. So this is x component of that vector. If this is vector A, this is x component of the vector, we call AX. I have traveled this length along x-axis, then we travel this much along y-axis. We can say this as AY, or also we can say this as AY. And from here I have traveled this much, and this is AZ. AZ, if I want to take projection of it, so I must do in the same way, taking parallel to this line, which is the projection of the vector on xy plane. So this gives me AZ. This becomes AZ. Okay, you can see both of them are of equal length. So this is how we decompose vectors. Now you can find out the angle this vector makes with each of the coordinate axes. So that part will go later on. So we can represent our original vector A as its component along x-axis as AX, plus we have taken AX plus AY. You notice that I am using AX, AY, AZ as vectors along XY and Z coordinate, XY and Z axis. There is another way of representing it, which is defining unit vectors along x, y and z. What does that mean? Unit vector means one unit length. It could be this much. Suppose we define 1 centimeter as one unit. So this is generally represented as I cap. One unit along y axis would be j cap. One unit along z axis would be k cap. So along x axis it is I cap. Along y axis it is j cap. Along z axis is k cap. So same vector I can re-represent using the unit vector and the magnitude of each component as this is now the magnitude. There is no arrow or bar on top, into I cap plus ay into j cap plus az into k cap. So now each of these unit vectors are defining the direction of the component, and ax, ay, az represents the magnitude of the component of given vector A along our preferred coordinate system.